So welcome to video section 2-2 in geometry. I am on page 18. This is my fourth video of this Sunday afternoon. It's actually now Sunday evening, and I'm getting ready to start dinner, so you might hear a little bit of beeping in the background. It's my oven. I'm presetting it to 350. So we are going to be in section 2-2 dealing with this concept of deductive reasoning. So deductive reasoning is kind of a different thing to think about. This, and I'm just going to run through some of the definitions. When we talk in mathematics, there are specific rules and methods in which we help people understand that something is true. And it's called rules of argument that we use to convince someone that a conjecture is true, even for beyond what we can see. And this is a very specific way of kind of proving what you're telling someone. It's just a different way of thinking. So these rules are called logical reasoning or rules of deductive reasoning. And that's when we're talking about these rules. Oh, my oven is ready. And it follows in a logical form called a proof. And when you guys talk to people about geometry and you say, oh, I'm in geometry, they're probably going to say geometry proofs. We will get there, but we are not getting there today. We are setting up the initial steps to help us understand what a geometry proof is. So a statement or a conjecture that has been proven without a doubt is called a theorem. A proof transforms a conjecture into a theorem. This whole paragraph is really important and huge. So we're going to walk through that. I'm going to reemphasize that vocabulary, and we're going to walk all the way through it. So over here in the academic vocabulary, it talks about an argument is not a disagreement, because that's our usual vernacular of the concept of the word argument. An argument is a series of reasons or facts that support a given statement. Okay? So when we talk about a conjecture is, sorry you guys can't see that, is a prediction. When we talk about a theorem is a conjecture, a prediction, oh, my laundry is done, a prediction that we take and we basically prove true with arguments. Okay, so we're going to walk through some of this. So here we go. Couple of vocab things. An even integer is a remainder of 0 when divided by 2. So I would ask you guys, if we were in class, shout out some even integers. And people were like 2, 4, 6, 8, and so on. And an integer can also be negative. So we could have -2, -4, -6, -8. Integers are positive and negative counting numbers. We're not going to hit decimals and fractions right now. Odd, well, odd's not even. So like 1, 3, 5, 7. Odd, when it's divided by 2, has a remainder of 1. You might also wonder, is 0 even? Yeah. Yeah, because 0 divided by 2 is 0. There's no remainder. So we're going to take a look at calculating some sum of pairs of even integers. So if I were to say, hey, toss out 2 even integers, 2 and 4, and that makes 6. And someone might be like, okay, can we get more creative? What about -100, also even? And 12. Okay, now you guys are going to make me do arithmetic, and you're thinking, you're the one that made up the example. It's your own fault, lady. Okay, it is my own fault. What is that, 88? So when we add together, sum means to add two even values, we get even values. So let's make a conjecture about the sum of 2 even integers. I'm going to say that even plus even equals even. I think that seems to fit. Calculate the sum, I'm on part 2, of pairs of odd integers. Okay, So let's do some odds. 1 plus 3. Well, that's 4. Remember, sum means to add. Let's do negative 11 plus negative 3. That equals negative 14. What if I did negative 1 plus 13? That equals 12. So I'm noticing that odd plus odd equals even, if I could spell and write. So now number 3 says calculate pairs of integers where one is even and one is odd. So let's do 4 plus 1, an even and an odd. That gives me 5. Let's do negative 10 plus negative 3. That's negative 13. Let's do 6 plus negative 9. That's negative 3. When I do even plus odd, I get an odd integer. Interesting. Okay, we're going to use that. We're going to scoot over here to the next page. So now what we're going to do is we're going to start working with arguments, reasons. And in this, we have already pre-drawn, which is kind of nice. We don't have to take the time to do that, 4 different figures. So if we were to count all the little boxes, 1, 2, 3, 4, 5, 10, figure A is a total of 10, figure B is 6, figure C is 11, figure D is 13. So can we say that figure A is even, figure B is even, C is odd, and D is odd? Well, which of the figures can be used to model an even integer? A and B. An odd integer, C and D. Now compare and contrast the models of even and odd integers. Well, an even integer, to me, I see that that creates a perfect rectangle. An odd integer has one extra box on the end. Okay, that works. So now it says, which pairs of puzzle pieces can fit together to form perfect rectangles with no extra piece on the end? Can we agree that A and B, now this is not going to be perfect. I told you it wasn't going to be perfect. There's figure A at 10 and figure B at 6. If we were to put them together, we would have if I added that correctly, a beautiful rectangle. Can we agree that if we were to slide together picture C and picture D, so C plus that piece, and then D we would have a rectangle that slides together to fit. Okay, so hopefully that makes sense. Those little overlaps would need to click together. Let's continue on in our conversation of deductive reasoning. So explain how the figures can be used to show each of the conjectures in 1 through 3 is true. Well, couldn't we say that we're showing even plus even equals even because it makes a box or a rectangle without an extra piece, and that that odd plus odd equals even because the 2 extra pieces form a rectangle, and that even plus odd would equal odd because we would still have one extra piece. Okay, because they don't fit together like that. So we've actually just proven conjectures because we've given reasons that we can't argue because they're factual and they're correct. And so we're going to take another step and we're going to start reasoning abstractly. So it says use the expressions 2p and 2m, where p and m are integers, to confirm the conjecture that the sum of two integers is an even integer. So if I were to take 2p plus 2m, so it doesn't matter what p and m are, they're generic. If you double something, you're always going to get an even number. Well, we could rewrite this as 2 plus p, or 2 times the quantity p plus m. This will be even because 2 times something will always give you an even value. Now if we come down here to number 8, it says let's talk about odd. So notice how we're going to do 2t plus 1. That plus 1 is like something hanging off the end. So could we use expressions to show two odd numbers? Yeah. Let's do 2t plus 1, and let's do another one. We're going to name it n. Okay, well, we don't really need those parentheses to protect those expressions. And we could combine like terms. We could factor out a 2, and you're like, oh my gosh, factoring? Yeah. Check this out. In here, this guy's an odd because we have that plus 1 on the end. And times 2, 2 times anything, makes this an even value. Interesting. So odd plus odd makes even. We could do the same thing over here where we start talking about expressions for even and odd integers. So if we were to do 2p, that guy's even, plus 2t plus 1, that guy's odd, and we were to drop those parentheses around those expressions, I'm hoping we could see that was supposed to be a t. I don't have any whiteout. That we still have this plus 1. Even plus odd is going to be odd. So now we're using algebra to do this. I'm hoping that now you guys have seen the give me the examples where we're kind of looking at patterns, even and odd and all of that. The others where we're using geometric models with the shapes, and now we're doing algebra. So let's skip number 10 and let's come down here to number 11. State 3 theorems you proved. I think we can say even plus even equals even. Pretty confident we can say odd plus odd equals even. And we can say even plus odd equals odd. And you'd be able to see that if my equipment would focus. All right, so let's turn the page. So let's pop over here. We're going to do some of the check for understanding. I'm going to try to go through this relatively quickly, and then you guys can work through the rest. So number 12, compare and contrast a theorem and a conjecture. And I know it's fuzzy, it'll clear up. A conjecture is a prediction. It's an idea. It's a suggestion. Come on, clear up, document camera. Here we go. A theorem is a proven conjecture. Number 13. Todd knows that 3, 5, 7, 11, and 13 are prime numbers. So hold on, what's a prime number? A prime number is divisible by only itself and 1. Okay, so 2 is also prime. But Todd says, based on what he sees of 3, 5, 7, 11, and 13, he thinks all prime numbers are odd. Is this an example of inductive or deductive reasoning? Well, this is inductive reasoning because he's looking at his pattern. He hasn't proven it. And is Todd's conclusion correct? No. The number 2, when you think about the definition, is divisible by only itself and 1. Well, that's even, and it's also prime. So real quick, is the number 9 prime? It's odd. No, it's not prime. The number 9 is what we call composite because it is divisible by 1 and 3 and 9. Okay, let's take a look at number 14. We're going to zip through this. Shayla knows that all rectangles have 4 right angles. So Shayla is on the right track here. We have 4 right angles, those perfect corners, even though I can't sketch that well. She knows that figure ABCD is also a rectangle. She concludes that figure ABCD has 4 right angles. So is this inductive or deductive? This is deductive because it's based on proof. It's based on fact, not a pattern, but factual definitions. Is Shayla's conclusion correct? Yes, it is. So there we go. There are some examples of deductive reasoning. Assignment is coming soon. You'll find it in Google Classroom. Let me know how I can help. Bye.